All right, so it's great to be here. I want to thank the organizers of Astronomy on Tap for the invitation. They've offered it several times. I've finally been able to accept it, and they were great with the logistics. They deserve a ton of credit working with people like me who are completely disorganized. So I appreciate that for all of this. A little bit more about myself. I've been doing this a long enough time that, yeah, I'm tenured. I'm at the other Texas university. We can tell jokes at intermission. I've got some doozies about Aggies, which is interesting in its own right, but we'll come there later. So one of the things I got to do while I was a graduate student is work with the Hubble Space Telescope. I was in Baltimore. That is where they host the Hubble Space Telescope Science Institute. And while I was there, it was just a couple years after they had done the first servicing mission on Hubble. They had cleaned up the optics to the point that it was actually giving us an unprecedented detail of the universe. And for the first time, we were seeing these structures that no one had ever seen before, been able to. It had this incredible resolution showing us details about galaxies and about nebulae that we'd never seen before, and it was easy to get sucked into that. I've been doing it ever since, more years than I realized most of the time. Hubble is much older than, I'm going to guess, many people in this room, and I think it's one of the trivia questions, so we might come back to that later. But I'm going to tell you some of the work we've been doing to understand how galaxies form, how galaxies have evolved, like our own Milky Way. So I'll start with that. All right, so for the uninitiated, this is an image of our Milky Way. And if you're far away from city lights, you can see this on a dark night. If you're in West Texas, far away from Austin, you can find this. It's that white band of light that stretches across the sky. It actually is, people have known about this forever. The Romans called it Via Lactea, which actually means way of the milk, hence the Milky Way. And what you're seeing is the collective light of literally billions of stars together. You're no longer seeing so much individual stars as you are their individual lights spread out across the sky. The dark clouds in front are actually not clouds like you would expect here on Earth. Those are parts of gas and debris in our own Milky Way from which new stars will form. It actually blocks the light of things behind them. This is a very privileged view taken here on Earth. It's actually taken from South America and Chile on a mountaintop. That thing right there is the silhouette of one of the large telescopes we have down there. And the most important thing about that is I'm actually in that telescope when this picture was being taken by my friend Wapu Rajapakarn here. This is that privileged view. The southern hemisphere of the Earth actually points more into the center of our galaxy, so you can begin to see the central region where the density of stars is so much greater than it is out here. The sun actually lives in kind of a rural part of this galaxy. So this is the view from Earth. This is the view of this galaxy now taken from space, a very privileged view, in fact. You're seeing the collected light from 3 years from a satellite that the Europeans launched called Gaia to study how our Milky Way galaxy formed, to study the stars it contains. There are in this image something like 1 billion stars. Again, you're seeing mostly the unresolved light from those stars in the center here, and they stretch themselves out in a nice plane. This is oriented so it has a galactic north pole, just like the Earth has a north pole, galactic south pole. They stretch out east and west along here. And we realize a lot of things already. One is that our sun, well, we've known this for a while, sits about 24,000 light years from the center of this galaxy. It's way out in the boonies. The sun is so far out that we're in a region where there aren't many other stars. The nearest star to our own is about 4 light years away. In the central part here, you're actually seeing this nice large protuberance. The density of stars is so much greater that the nearest star might be a fraction of that, 10% of that distance, maybe much less than a light year. So in the center part, you would have a much different view of the night sky. You would see much brighter stars in addition to your own sun, for example. So we sit way out here. We know this galaxy our own galaxy has this nice protuberance, this big bulge. We know there are many billions of stars in this image, but it's very difficult to interpret how we formed. For example, we can only see maybe 1% of all the stars that are in the Milky Way. Because it's in this disk, and our own sun is one of the many stars in this disk, our view is obstructed of what the whole galaxy looks like. So instead of trying to study this, we go to other galaxies that we think might look like our own. This is a relatively nearby galaxy. Now you're seeing a Hubble Space Telescope image of it. It has a name, NGC 3982. It's actually the new galaxy catalog. It was new about 250 years ago when it was cataloged by a guy named William Herschel. There's a good joke about that. William Herschel discovered Uranus. We can come back to that. Yeah, okay. That's Aggie humor. Okay, here we go. Yeah, okay. I heard that, strangely. Okay, so when we look at this image, we find it has a lot of the similar characteristics of what we see in our own Milky Way. It's relatively flat, but now we're looking down on it, which we can't do with our own galaxy. We're stuck in it. The image shows us other things. You see this blue light out here. That tells us this is where new stars are forming. And the reason is the following. Those regions contain stars that are much more massive than our own sun. When stars are born, they're born with a range of mass. You get high mass stars, you get low mass stars. But the high mass stars, because they have more mass, they burn hotter. They burn through their fuel much faster. And as a result, they're very short-lived, and they don't last very long. 10 million years, 100 million years, then they're gone. So the fact that we can, and those are very short time scales for astronomy. So the fact that we can see those blue regions tells us that's where stars are forming now. We also, you might see, if you squint closely, these little purple regions. These are regions where the stars are actually being formed. They're deep gas clouds, that's where we said stars form. They're still inside their gas clouds, and they've yet to emerge. All their light is being absorbed by the gas and debris around them, and it's coming out these redder wavelengths that we see, and your eyes pick that up. So we see, way out here in these spiral features of this disk, that stars are forming today. That's very different than what you see in the central region. What we think is exactly the same in our own Milky Way, these would be different. These are some very smooth distribution of light. You see it has this yellow-orange color associated with it. These are stars much more like our sun. They're stars that last for billions of years. There's no more star formation in the center here. It formed maybe 10 billion years in the past. And this shows us that. We can see this with the color. These are the longer-lived stars, like our own sun. Our own sun is maybe halfway through its 10 billion year life cycle. These are much more longer-lived stars. And so the colors tell us a lot about this information. A lot of this information about how a galaxy like this formed. This tells us that the stars here would have formed much longer ago, and we're only seeing these lower mass, longer-lived stars. They just burn cooler, so they last a lot longer. And over time, we're seeing the stars are now building up in this outer region. So we can begin to paint a picture for how we think this formed. In fact, this is where I'm going to take you for the rest of this, is how we think this formed. So we can zoom out and think, what would this have looked like in the past? And we think that around 5 billion years ago, right around the time our own sun was forming, the galaxy may have looked more like this one. This is another Hubble image of an actual galaxy. Here you see it's smaller. I've actually put them on the same size scale. So they would have this, this is how they would appear if they were right next to each other. Here we still see it has this bulge and protuberance, and it still has that yellowish-orange color. We haven't yet hit that point when stars would be forming there. Instead, the stars still appear to be forming out in this outer region out here. 7.5 billion years ago, we can find another galaxy that looks like this. And here it's getting smaller still, just size-wise. It's not quite as big, but we haven't quite hit that point where the center regions are forming. Not until about 10 billion years ago when the colors start to turn whitish. And that tells us we're seeing those stars, we're seeing the massive stars that indicate very recent star formation, and the bulge, the central region is beginning to form. We can push this out to 11 billion years, almost 12 billion years with the Hubble Space Telescope, and I'll show you some of that. But then that's about the limit to which we can see the babies of a galaxy like our Milky Way. Beyond that, they're just too faint and too small. Okay, so what do we do for this? Well, this is of course the iconic image of the Hubble Space Telescope. Hubble Space Telescope this year is 28 years old. It turned 28 in April since its launch. I've realized then that I've been at Texas A&M so long that all of the students I now teach as undergraduates and many of my graduate students are younger than the Hubble Space Telescope. This telescope could legally drink at this bar. I'm not going to ask if everyone else here can legally drink at this bar, but the Hubble can. They upgraded the optics in 1993, and that's when it began to give us this crystal clear view of the universe. But there's a trade-off. You're in space, you're above the atmosphere, and the atmosphere creates turbulence that interferes with our ability to observe things with ground-based telescopes, but not the Hubble Space Telescope. It's above that. That's what gives it that crystal clear image of the night sky. The problem is, when you look with it, you see a very limited field of view. What does that mean? That means, well, with your eyes, you have a very wide field of view. When you look at the night sky, you see all of these constellations. If you've been to a movie theater, you've seen probably this one, Orion. It has the belt, it has the scabbard, his bow is supposed to be out here somewhere. I don't really know, it's somewhere like that. Here are the Pleiades. I'm an astronomer, right, okay. Here's Sirius, it's the brightest star in the sky, besides the sun. Somebody always points that out, the sun is brighter. This is the next brightest star. you can see all of this. They're separated by many degrees on the sky. They're 360 degrees in a circle. You can see many degrees in the sky with your eyes. The Hubble, when it looks, sees that. In fact, you can't even see how small it is. That's bigger than the size the Hubble Space Telescope can give you. And to give you an example of what the Hubble can actually see, I'm going to show you that. That, I hope, is recognizable to you as a dime. And there is someone's bust, a head, face on it, at least until they replace it next year with that of the current president. I'm kidding, that was a joke. Oh, wrong audience? Okay, too soon? Okay, sorry. Just wait, just wait. That is, of course, President Roosevelt is on the dime. Somebody said Eisenhower last time I gave this talk, and I was like, really? It can't be Eisenhower. Okay, so that's President Roosevelt. And if the field of view that the Hubble can see, if you take a dime and hold it at arm's length and then give it to me. No, if you hold it at arm's length and you look at his eye, that is about 2 minutes of arc. It's about 1/20th, 1/30th of a degree. That is what the Hubble Space Telescope can see. If you have 20/20 vision, you can barely resolve that at arm's length. You can barely differentiate that there's a size to that. It looks like a point to you. That's all that Hubble can see at one time. Of course, we take Hubble, we point it in blank regions of the sky, Hubble images this for very deep periods. There's nothing else here. You would see nothing. No telescope telescopes on Earth can start to see it. Hubble sees this. There might be thousands of galaxies in a single image with Hubble. They have a myriad array of colors, and you begin to see most of these things are very distant galaxies. One thing you'll find, one thing we know, is that light travels very quickly, but it's at a finite speed. And so we don't see these galaxies as they are now. We see them as they looked when the light left them. And so it gives us a snapshot of what they looked like in the past, what the universe looked like in the past. And so as you look to more distant and distant galaxies, what you actually see is a snapshot of them growing. They're in their infancy. You're seeing them many billions of years ago, what they looked like. One of the things we noticed with Hubble, and you might be able to see with this picture early on, when I was still a graduate student, is that the fainter galaxies start to appear bluer. This was called the faint blue galaxy problem when I was a graduate student. They're more distant. People realized that blue color tells you they're forming stars much faster than they are today. But it began to give us an idea that galaxies in the past were forming stars and growing much faster than they are now. So we have to put this together. So here's an image of Hubble that Hubble would take of an actual galaxy. This is what you might see. You can kind of see it as a nice spiral pattern we saw before, and it has some little clumps on it here. Hubble, of course, doesn't take an image at one wavelength. What we do is we take images across the range of wavelengths that Hubble can observe. That would be here. And I've put some numbers down here. These are the actual wavelengths of light that you can see. And of course, you start to pick up very different features when you do this. Your eyes are tuned to observe around that range, from about 400 nanometers to about 700 nanometers. 400 to the untrained eye looks blue. I, of course, see 400. Many of the astronomers see 400. Most of you probably see blue. And if you look at 700, 750 nanometers, you see red. I just see longer wavelength light. With Hubble, we can actually see over this whole range of wavelength. And now we can start to see it gives us a different picture of what's going on in a galaxy like this. We can make nice, pretty colors. NASA's really good at doing that. But this is what it would look like if I combine the light at these shorter wavelengths, these bluer wavelengths, and if I combine the light at these redder wavelengths, you get a different picture. What you're seeing then is an image that shows you bluer light. This is the locations of these massive, short-lived stars, the ones that are going to burn out very quickly. It shows you where stars are forming now. This image over here is showing you the longer wavelength light. These are from stars that are lower mass. They last for billions of years. And it shows you where stars formed in the past. And we actually take data like this. We take a vast range of models, and we begin to figure out the history of how stars formed in galaxies like this. And we do it across cosmic time to begin to build up a picture for how galaxies like the Milky Way formed. So we're going to come back to this image of the constellation. Hubble observes in that little crosshairs down there with that little label on it called Goods South ERS. There's a point to that. Starting around 2011, I was part of a team of astronomers. We had proposed and received the largest allocation of time ever with the Hubble Space Telescope. They had just upgraded Hubble. It was the last time they will ever upgrade the telescope with brand new near-infrared cameras, and they had upgraded all of the detectors, all the batteries, the solar panels. Everything was new. It was like having a new telescope. And we began to image large swaths for Hubble of what we actually could. I'm going to move it up a little bit, and then we're going to begin to zoom into this. Remember, we observed intentionally a blank patch of sky so none of these silly constellations or stars get in the way. And as we go in, we'll begin to see this vast arrangement of galaxies. We're still not there. Starting to get there. Now we begin to find them. And again, the nearby galaxies, we're seeing them as they looked relatively recently for astronomy, maybe only a few billion years ago. They'll look fully formed. They have these spiral arms, they have nice large bulges. As you look to the fainter ones, that's when they're farther away. They're more disheveled. They're forming stars at a very rapid rate. What we do then is we take these images. We're seeing that at different colors. We're seeing them at all these different wavelengths. We begin to model them with computers. That's where the magic of data science happens. So we might take an image like this, and we'll process every galaxy to begin to build up this history. What we really want to know are, well, there are many things, but three of the main things we want to know are, how far away is the galaxy? How fast is it forming stars now? And how many stars has it already formed? Because that tells us something about the history that it's had. And so we'll start with a galaxy like this. There it is. And your eyes will begin to tell you this. I'm beginning to train your eyes. You have this yellowish-orange color in the center. You're going to know those are older stars, ones that formed a long time ago. You're going to see, and that's where the mass is. You're going to see that bluish region of the outskirts. That's where the stars are forming. We feed all this information into supercomputers and model it with copious amounts of variables. And what we do is we add up the light from different populations of stars, ranged over a vast range of star formation histories. We throw in the fact that some stars are born in deep clouds that are heavily extincted. We find every supercomputer we can get our hands on. They have something called the Brazos cluster at Texas A&M. We've used TAC here in Austin. We've even experimented with Amazon Web Services. When you guys aren't busy buying things during my talk, they will rent you out their supercomputers. I think it's $1.50 an hour. It doesn't sound very much, but it racks up pretty fast. Because we have thousands of galaxies. We might even have tens of thousands or 100,000 galaxies. Actually, we're getting to about 1 million galaxies now per run. The number of models we have will be something between 10 million and 1 billion per galaxy. So it takes 1 to 100 seconds, even on a supercomputer, to process it. But you can parallelize this up the wazoo simply because each galaxy is a separate thing, so we just fire it off as many processes as we get our hands on. And we do that, we actually discover things. Like for a galaxy like this, your eyes were correct. This galaxy turns out to be about 6.3 billion light years away. It has the mass of our own Milky Way galaxy. It's already achieved that mass, and it's forming stars at a rate that's 20 times that of our Milky Way. So this is still growing. Even though it's already formed the mass of our Milky Way, it's still already growing. We can find more distant galaxies. You got to look over here in the corner. Actually, I'm sorry, this one's at the same distance. I know because I peeked ahead. Okay, this one, your eyes are now going to tell you different things. This one, there is no blue light coming from it. This is a galaxy that has formed all its stars. That yellowish-orange light means that all the stars that are left are the ones that are living for billions of years. And, of course, the models tell us the same thing. This one is also 6 billion light years away. It has formed the same mass that is in our Milky Way galaxy, but its current rate of stars, SFR stands for star formation rate, that it means it's forming stars less than the rate that our own Milky Way is now, even though we're seeing this galaxy 6 billion years in the past. With Hubble, we can go much farther in the past. Here's another one. Now, of course, we're seeing that blue light. In fact, you'll see some of that magenta color that tells us that stars are still forming in their nursery clouds. They haven't yet emerged fully. This one, the computer will tell us the same thing. It's 8 billion light years away. It only has 1/10 of the mass of the Milky Way, but it's forming stars 35 times the rate of the Milky Way galaxy. One more. This one is now farther away, and you get that deeper red hue in the center. That is an indication not of older stars, longer-lived stars, but the fact that in the core of this galaxy, stars are still in their birth clouds. And most of what you're seeing is the fact that they haven't yet escaped from that. That's what we need the computers to help tell us. This one is 10 billion light years away. It's formed half the mass of the Milky Way galaxy, but currently forming stars at 200 times the rate of our current Milky Way. You're catching it in a rapid growth state 10 billion years ago. So we can take all these galaxies, put them together, and start to build up a picture because we have snapshots of what they looked like throughout time. And we can begin to build them up to ask a question, what would a galaxy like our Milky Way look like? And we'll start in the distant past. Down here is billions of years ago, and I'm going to show you snapshots of what we think the Milky Way itself may have looked like. This is how we build up the galaxy like our own Milky Way today. So in the past, 12.5 billion years ago, this galaxy had maybe 3% of the mass that the Milky Way has. We're catching it in a very early growth stage. Imagine what a human looks like when you only have 3%. If you weigh 200 pounds, that would be 6 pounds of a human being. That's a newborn. As it grows, you're seeing that deep white color. The star formation rate here is spiking. It's growing very fast, much like an infant child does when you feed it. If you don't feed it, you get a phone call. Okay. So it grows very rapidly here. In fact, it goes from 3% of its mass up to 30% of its mass in relatively a short time for astronomy. This is over a few billion years. But about 3 billion years, it grows a factor of 10 in size, just like a newborn child does. As we go over, say, the next 5 billion years, it does grow, but maybe it only doubles its mass again. Instead, what happens is the stars have formed, but now the size is beginning to expand. So we're not seeing a lot of mass growth per se, we're seeing a lot of size growth. The inner parts have already formed, the outer parts are catching up, but most of the stars in this galaxy have already formed. The last stage I'll show you is here. This is the one I actually showed you at the beginning for what we think a Milky Way type galaxy would look like right around the time the sun formed. Our sun would have formed right around here, about 24,000 light years away from the center of this galaxy. Most of the mass in this galaxy is in the center, and it formed long ago in the past. And in fact, when we measured this for the first time, we realized, and NASA wrote some nice things about it for us, that our sun, because the rate that stars are forming are slowing down so much, we see this nice curve. It's much more rapid here, and it slows down. Our sun was formed just at the end of this major growth period of a galaxy like our own. We caught it on the tail. Most of the stars in the Milky Way formed much longer in the past, and they're in the center regions, not out here in the boonies. Okay, so where do we go next? Well, this is about what we can get with the Hubble. There are two things we don't know. One is, do all Milky Way-like galaxies grow this way? And what happened at earlier times? The next generation of telescopes should tell us. They should tell us, are there galaxies that grew later? They were late bloomers and they caught up at later times. Are there ones that formed all their stars first and then grew this way? Those are questions we don't know yet, and we hope to with the next generation of telescopes. NASA's launching two. The first one I'll mention is WFIRST, the Wide Field Infrared Space Telescope. It should launch in the mid-2020s. It's actually a telescope the same size mirror as Hubble, but it's a much more compact design. And NASA was given this as a hand-me-down from something called the National Reconnaissance Office. Apparently, they have Hubble-class telescopes sitting in a warehouse, and they said, hey, do you guys want this before we throw it away? And so NASA figured out what to do with it. And what they're going to do is make a Hubble-class telescope, but because of the compact design and with some intelligent people designing it, you get a field of view that's 200 times the size of Hubble. To give an image of that, here's a Hubble image of one galaxy cluster. I don't have time to talk about this. I don't think anybody else here today is either. But it's a dense city of galaxies that are all gravitationally bound to one another. Amazing amounts of dark matter associated with it. And as you zoom out, that is what Hubble can see. This is what WFIRST will be able to see in one pointing. You get a field of view that's 200 times the size of Hubble. So the amount of statistics we will have in the galaxy population goes way up, and we'll begin to search for that variation in how Milky Way type galaxies would have formed over time. Oh, you're right. I should have flipped it over. Good point. Okay, yeah, good point. Okay. Next time I'll do that. Yeah, thank you for pointing that out. Okay. The other telescope, of course, many of you should have heard of. It's been in the news recently. Is something called the James Webb Space Telescope. Yes, of course, here it is. Okay, so this is about 3 times the size of Hubble's mirror. It's also optimized to look in the near infrared. That will allow us to push to much fainter objects. They have less light. Well, this can collect the light. That light will be redder because they're moving away from us so fast, and this will be able to detect them. This telescope will be fantastic. The problem is you'll see how many moving parts there are in this telescope. Moving parts makes NASA very nervous, especially when there's no one there who can go fix it. The graduate students who have volunteered for this, we'll come back to them later. Maybe some of you who need jobs can go and apply to ride along the telescope and force that sun shield open when it does so. But this will allow us to see perhaps those first infant stages of a Milky Way type galaxy forming, the actual birth of such a galaxy. Okay, with that, I'm going to leave up a nice image of another Milky Way galaxy, and I'll be happy to take questions now or later. So, okay, thank you.
All right, thank you, Space Ventura, Galaxy Detective. All right, we have time for a couple questions. The first one will be from Twitter. Madison on Twitter asks, is the Milky Way still growing?
Is the Milky Way still growing? Yes, that's a great question. And yes, it is still growing, but at a much lower rate than it was in the past. So in the past, we think it would have been forming stars maybe 20 suns a year, 30 suns a year. A year is a very short time for a Milky Way type galaxy. But today it's maybe forming 1 or less star per year. So the rate has dropped by a factor of 20 from its peak to now.
All right. Question right up front, right there.
Oh, a very good question. So the question is, do we observe any similarities or correlations between the type of galaxy we observe and their rate of growth? That's a really good question. I mean, that's something we debate, so I'll give you my answer, and you can ask somebody else for their answer. So the answer is yes, we do see. Some of them are very obvious. The ones that have the smoothest distributions of light, they look very symmetrical. They tend to have the ones that are the lowest forming stars today. The ones that look very disheveled, very irregular, are forming stars at the highest rate. Does that answer your question? Okay, good, yeah.
All right, next question. Gentleman in the light blue right there.
So the images you showed had a lot of blue galaxies. Are those corrected for redshift or are they natural?
Excellent question. So the question is, did we correct for redshift? So one of the issues with the universe is expanding. As galaxies expand with the universe, their light gets shifted to redder wavelengths. Yes. So in fact, some of the images I showed did have them corrected for that redshift, just for that visual effect. When we run the computer models, we absolutely have to take that into account. That's actually what gives us the distance estimate we have to them. That's a really good question.
All right, lots of excitement. I'm going to look, okay, up on the top in the back.
What was the reflective material on top of the new satellite?
Oh, really good question. You're asking about James Webb and what the material was in the telescope? I should know the answer to that. I'm going to get it wrong. The mirrors are beryllium. I'm going to look for somebody in the back to nod their head. Are beryllium, and there are a couple ideas. One, it has to be able to reflect infrared light really well, and it has to not corrode. And so there are a couple, and it has to be lightweight. I mean, so they have to take all that into account. Were you asking about the mirror, or were you asking about the sun shield, the big basketball court-sized thing? Whatever expanded beyond the satellite. I'm going to have to pitch that one to somebody who might know. Are they made of gold? Nylon? Mylar. So it's made of mylar. And I'm going to take credit for that answer.
That was an excellent answer. Excellent answer. Okay, time for one more right here.
So the sun forming in the latter part of our galaxy's evolution, so a lot less energy. Do you think that impacts the planetary evolution?
Oh, that's a good question. So the sun forms very late in the history of star formation in the galaxy. A lot less energy out where we are. Would that have impacted planet formation? I think that's a debated topic. Certainly would be easier for stars out in the boonies to hold on to their planets, and at the same time, we are recipients, benefactors of all of the previous generations of stars that have generated all the nuclear fusion products like carbon and oxygen that have then seeded the clouds that would form systems like our own. So in a lot of sense, yes, but I think that's a hotly debated issue right now.
Okay, let's thank Professor Casey.
I'll be around intermission.
Yeah,
okay, thank you.
Professor K.B. Papovich one more time.
Thank you all.